Today's video is about computational thinking. So computational thinking is a way of problem solving. To be successful with computational thinking, it's going to use a combination of logic and maths. And there's three methods of computational thinking that we're going to have a look at today, which is abstraction, decomposition, and algorithmic thinking. So the first fancy word we're looking at is something called abstraction. And as a definition, it's removing unnecessary parts of a problem so that you can just focus on the main problem. Now that's a really common question that comes up on your paper 2 exam as a definition. It's usually a 1-mark question and this is the answer. So to actually use abstraction, you need to work out what is relevant in the problem and then what's not relevant. So you get rid of anything that's not relevant and then you can just focus on the main problem. Now this is especially important when you're thinking about programming. Sometimes people have great ideas and they'll spend a long time with their programming trying to do it. If that's not actually solving the initial problem you set out to do, then there's just no point in doing it. So you just need to be able to focus on the main problem, not get distracted, and remove anything else that's not necessary. Another really common exam question is they'll give you a scenario and you have to use abstraction to say what's relevant in that scenario and what's not relevant. If we just stick to the same rules that we've already talked about, then you just need to think about what the scenario is, think about what it's already told you that is going to be relevant in solving that problem, and then anything that's not, you can just say you've got rid of that. You don't need to focus on that anymore. The next part of our computational thinking is called decomposition. Most people seem to remember this definition because it reminds them of a dead body. And if you think a dead body is going to decompose, it's kind of the same thing where it's going to break down into smaller pieces. And it's the exact same thing with our problem solving. If you started with a large problem at the top, you might want to break that down into smaller problems so that it's easier to deal with. As general benefits of decomposition, if you're going to distribute these small problems to other people, it's going to get solved faster. And also generally smaller problems are solved faster on their own. And they will all feed into solving the overall main problem. So if you combine this with abstraction, you've already picked out what's important and removed anything that's unnecessary. And now that you've got that, you can break that down into smaller problems and then distribute that to a team of people who can work on it. The final piece of our computational thinking is called algorithmic thinking. As a definition, an algorithm is a set of instructions that you can follow to solve a problem. Quite a lot of time in lessons, teachers use the analogy of making a cup of tea, and then they'll talk about having those problems in the correct order to successfully make your cup of tea. For your exam, there are different methods of algorithmic thinking where you can show logically the steps of your problem solving. We're going to have a look at these in the next video, but the methods are going to be flowcharts, pseudocode, high-level programming, and exam reference language. Okay, so we've got a practice question for this topic. So a library has a computer system to record details of the books it has. Each book has the author, edition, book title, year published, and how many times it has been borrowed. Each book is given a rating based on author and how many times it is borrowed. This is quite a lengthy scenario, but this is the kind of thing I'm talking about that's been common in previous exams that you might get, and you have to use abstraction on this scenario. So I know there's a lot of information to take in here, but you might want to pause, you might want to have a look and maybe think about what's going to be relevant for these answers. So question 1, define the term abstraction, just a simple definition. And then question 2, give one example of how abstraction is being used in the design of the rating system. Okay, let's look at the answers then. So question 1 was define the term abstraction. So it's focusing on the main parts of the problem, removing unnecessary detail. And question 2, give one example about how abstraction is being used in the design of the rating system. So they're focused on the author and the title and how many times it's been borrowed. You can ignore the year it's been published and the edition. It's told you that in the scenario what the rating is based on.
Today we are looking at writing algorithms. So there's different ways of writing an algorithm, but we are going to focus on both flowcharts and pseudocode. It's worth mentioning that we can write them in a high-level programming language like Python, and there's also exam reference language, which OCR have got their own, but we're not going to look at that, purely because you can still get the marks in writing pseudocode or high-level language. Writing an exam reference language is almost like learning an extra language on top of that. In my opinion, stick to learning less and you can still get full marks. So when you're writing an algorithm, they should always include input process, and output. An input will usually come from the user. They might be prompted to type something in. It could be an integer, it could be a string, and so on. Most of the time that input is then stored in something called a variable so we can do something with it. So that's where processing comes in. The value might change, other values might change, and if there's any maths going to happen, then this is the time when it will happen. Finally, you will display what you've done to the user. That's usually so they can see that it's worked, whatever they've tried to do. We're going to start by looking at a flowchart example. This flowchart doesn't use all of the symbols possible, but we will be going over those as well in this video. So to begin with a flowchart, you always use an oval at the very beginning, which we've just written the word start inside it. To show the direction of flow, we use arrows between the different symbols. Now this flowchart is going to be checking a username and password to log into a device. So because the user is going to be prompted to type in their username, we've written that into a parallelogram and we've written inside it input username. Username in this case will be used as the variable which will store whatever they've typed in. In a separate parallelogram, we're then going to allow the user to type in their password. This will be stored in a variable called password, but again inside our parallelogram we've written input and then password. Following on from this, we've got the decision symbol. This is the diamond shaped symbol. In this decision symbol, we are going to check if the username is correct. So to do that, we're using the exact word that we used before to store it, which is username, and we're asking a question. Is username equal to Mr. Moore CS? Now you'll notice that I've got a double equals sign in there. That's not a mistake. That's to do a comparison to see if it matches. So if the answer is yes, it will move on to the next decision symbol. But if the answer is no, it's going to display a message, which is our output, and it's going to say to them, try again. And following our arrows, it's going to loop back to allow them to type in the username again. But if the username is correct, then we're going to move on to our decision symbol, which is going to check the password now, asking the same kind of question, is the password equal to cool beans? If the answer is no, it's going to output the message, try again, and just go back to the beginning. But if the answer is yes, it will display a nice welcome message saying output welcome. It's also not a mistake that we're using a parallelogram for an output as well. This is used for both an input or an output symbol. Following that, we've just got an end because that's the end of our algorithm. Another symbol that's quite common that we're going to talk about is called the process symbol. So your process symbol is used for any instructions or any actions that just take place as part of your algorithm. This would include assigning variables. If your variable isn't an input that the user is typing, you can do it separately in a process symbol like this. In this example, I've got two variables that have been set. We've got num1, which is equal to the integer 5, and num2, which is equal to the integer 10. Another example you can do is any calculations. Let's say in an algorithm we wanted to add the two numbers together. So I've got a new variable which is called total equals num1 plus num2. That kind of calculation that takes place is going inside a process symbol as well. Another symbol we've got is called a subprogram symbol. Notice that this one looks just like a process symbol, but there's two vertical lines either side of it as well. Now let's say that you've got two flowcharts that are running alongside each other, but you only want one of the flowcharts to activate at a certain time. That's when you call a subprogram, and that's what this symbol is used for. If you reach a point in your flowchart where you want to call the other flowchart which you've got running alongside it, you can use this symbol. The other flowchart has usually got a name so that you can put the name inside this subprogram symbol, and then you can call the other one to activate it. Okay, now we're going to have a look at something called pseudocode. Now pseudocode is very similar to the English language, and it's actually usually very similar to Python programming language. Even if you're familiar with a different programming language, you should still be able to look at pseudocode and understand what it is trying to say and do. It's kind of like a universal language that even people from all different backgrounds can understand. Now there's two parts to your second exam paper, Section A and Section B. In Section A, it will say things like this: write an algorithm in pseudocode, and then you will put your answer. Where if it's in Section B, it will ask you to write in a high-level programming language like Python. So make sure that you read the question carefully so you know which bit it is that you're writing down in your exam. So we're going to work through this example together. This was a 3-mark answer on a previous paper. So it says to store hello, which is a string, in the variable word1. Then store everyone in the variable word2. Then we've got a programming word, concatenate word1 and word2. That means to just squash them together to store hello everyone in the variable message. So to do this, it's going to look very similar to what we wrote inside the symbols in our flowchart. So word 1 equals hello, word 2 equals everyone. Here's the concatenate part of it, where we've been told to store it in the variable message. So we're going to say message is, which is the equal sign, word 1 plus word 2. That's how you concatenate it. Now notice on this one, it doesn't actually output this to the user, but it doesn't ask us to do that in the question. So we just need to make sure that we stick to the question, don't add any extra functionality, and then you'll still get all marks. If you accidentally then outputted it to the user, maybe write in print or the word output because it's pseudocode, you wouldn't lose any marks for that, but you're adding extra unnecessary work to yourself, so I wouldn't recommend it. Okay, so we've got an exam question to practice. We're going to do a very similar to the one we just looked at. So look at the following instructions. Store the string good in a variable called word 1. Store the string morning in a variable called word 2. Concatenate word 1 and word 2 and store the result in a variable called greeting. Here's a little bit extra though. Store the number 3 in a variable called repeat. Then we're going to create a new variable, final message, by repeating the greeting repeat times. That's not a typo. Don't forget we've stored the number 3 in the word repeat. Okay, let's look at the answers then. We're going to store good in word 1. We've got word 2 equals morning. Then we've got greeting equals word 1 plus word 2. Don't forget that plus sign is your concatenate to squash things together. Then we're going to store the integer 3 in the word repeat. And then finally, we've got final message equals greeting, multiply, which is little asterisk, repeat. If you were interested, let's look at the flowchart version of that. Now, interestingly, unlike before, this has got all process symbols pretty much compared to what we didn't see one in our earlier example. So to begin with, we've got word 1 equals good, which is going in a process symbol. Word 2 equals morning in a process symbol. Greeting equals word 1 plus word 2, which is our concatenation. Because it's like a calculation, it's going inside a process symbol. We're going to store the integer 3 in repeat, which is another variable, so that goes in a process symbol. And then finally, we've got our variable final message, which is greeting multiplied by repeat. It doesn't ask us to output at any time, so we don't need to use our parallelogram. We can just end. Today we're going to be looking at trace tables. A trace table is a tool used so you can keep track of what a variable is doing as a program is running. It's quite often used if you're having any problems with your program and you want to figure out exactly the moment where it's not acting the way you want it to. So we're going to look at an example about what it might look like on your exam. Here we've got some pseudocode and we're going to write the trace table out for what this pseudocode actually does. So if we just talk about the pseudocode first, we've got two variables at the beginning. We've got counter and we've got total. So we've got a while loop here, which means it's going to repeat a section of our code. And in this case, while the counter is less than or equal to 5, it's going to repeat. And then as part of what happens as part of my loop, total is going to increase each time and it will output the total, which means it's going to show the user what currently the total is. And then we're going to add 1 onto the counter each time it loops. So with that in mind, this is our trace table that we're going to fill in. It's just going to store all of the values of the variables along the way and what the output will be. So to begin with, your counter is at 1. We're going to add 1 onto the total because that's what the counter currently is at. It's at 1 and the total's at 0. So in the total box, we'll put 1 and then the output is just going to be whatever the total is, which is going to be 1. Now notice on this column on the left hand side, it's called iteration, which means that's our first iteration of our program. Now we're going to do it again, but we'll see some different results. So the counter increased by 1, which means it's now currently at 2. But because we're doing total plus counter, we're going to do 1, which is what it's currently at, plus 2. So the total is now at 3, which means my output is also going to be 3. We're going to add 1 onto the counter and then start again. So for our third iteration, our counter is currently at 3. We add our counter to the total, which means our total is now at 6, which means the output is currently at 6. We add 1 onto the counter, and then we're on our fourth iteration. The counter is currently at 4. The total of 6 added to the 4 gives us 10, so our current total is at 10, which means my output is 10. We add 1 onto the counter, and then we're on our last iteration. So our counter is at 5. Our total was currently at 10, so it's 10 plus 5, which gives us 15, which means that the output to the user is 15. So this is what a completed trace table looks like. It would allow the user to see exactly what is happening with all of the variables and outputs throughout the whole program. If this wasn't what the user was expecting, at least they now know what's going wrong and how they can fix it. So we've got an exam question to practice. It's going to be quite similar to the previous one, but maybe slightly easier because we've only got one variable and one output that we are recording in the trace table. To begin with, we've got a variable called number and it is storing the integer 10. While the number is greater than 0, we're going to output whatever the number currently is, and each time it iterates, we're going to take 3 off our number. So complete the trace table to show the values of the number and output at each step of the loop. Okay, let's go through the answers then. So to begin with, we had number was at 10, which means the output was at 10. Then we're going to subtract 3 from the number, which means that the number is now at 7. So we output 7 because the number is currently at 7. We take another 3 off, meaning that the output will be 4 because the number was at 4. We take 3 off, and then we're going to put the output of 1 and the number at 1. That's when our while loop would finish, because while it's greater than 0, it was going to loop itself, but once we remove 3, it will be lower than 0, which means that's the end of the loop. Today we are looking at sorting algorithms. In terms of what a sorting algorithm actually is, it can sort information into a way that we want it to. There's loads of different sorting algorithms. Some of them are faster than others, but for the exam we need to know about 3, which is the bubble sort, the merge sort, and the insertion sort. We need to be able to describe the different kinds of sort. Sometimes you're asked to actually carry out one of the sorts, but sometimes you're asked to just describe one, or sometimes you're asked to compare one to another one. So we need to have a really good understanding about what each of them do, how they work, and then be able to carry them out as well. So we're going to start with the bubble sort. We're going to talk about data here and how data can be put into an order. It might be alphabetical, it might be numerical, and so on. Now for a bubble sort, we're going to start at the beginning of the list. That first value will then be compared to the next one to it, or the proper word that we're going to use is adjacent data. If the value in the first position is larger than the one next to it, it's going to swap. You will then look at it in the next position, and if it again is larger, it will swap again. Now it will keep acting like this and keep comparing to the adjacent data. If it isn't bigger than the next piece of data, then it will start swapping the next largest one, and so on. Once it reaches the end, there'll be no more checks to do on that, and that means that's one pass. So you'll be going back to the start of the list, and you'll do the whole thing again. You'll check the first position, compare it to the next piece of adjacent data, and so on. So we're going to have a little practice of this so we can see what it looks like. Here we've got some data which is not sorted. We're going to start by looking at the 2 in our first position. We're going to look at the adjacent data, so what's next to it. It's a 4, which is higher than 2, so it's not going to move. So then we're going to look at the 4 and compare it to the 1. Now 4 is bigger than 1, so they are going to swap. Now at this point, the 4 will be compared to the 5. 5 is bigger than 4, so there's not going to be any swap. We will then compare the 5 to the 3. 5 is larger than 3, so they're going to swap. Now we've done a full pass here, so we're going to go back to the beginning. So 2 is compared to 1. 2 is larger than 1, so they're going to swap. You can see it's actually nearly sorted now. 2 gets compared to 4. There's no swap because 4 is larger than 2. 4 then gets compared to 3. They're going to swap because 4 is larger than 3. And our data is sorted using a bubble sort. So let's look at the advantages and disadvantages of a bubble sort. So to begin with, it's easy to learn and code, especially for beginners. And it works particularly well on small or nearly sorted lists. At a disadvantage, it's a pretty slow sorting algorithm. Other algorithms like the one we're going to look at next, the merge sort, are much faster. Okay, let's move on to the merge sort then. This one uses a technique called divide and conquer. So when we start with our list of data, we first of all need to separate it all and divide it. You would then pair the individual elements and place them in order. They will keep combining until they reassemble and they're fully sorted. Let's have a practice with the merge sort then. Here we've got our unsorted data and we're going to start by dividing it. So we split them into 2 separate groups like this. We're then going to split them down even further. Finally, we're going to put them all into individual elements of data. Now we're ready to start the merge part of this. So 2 and 8 were already in order, so when they merge, they're going to stay looking the same. The 1 and 4 got compared. 1 is smaller than 4, so it's going to be reordered as 1 and 4. The 5 and the 3 we're going to get compared. So they get reassembled as 3 and 5. And then the 7 and 6 get compared and they get reassembled as 6 and 7. We then merge the green and the yellow groups together, which gives us 1, 2, 4 and 8. Then we merge the blue and the pink sections together, which gives us 3, 5, 6 and 7. To finish with, those two groups will get merged, giving us our list in order. So let's look at the advantage and disadvantage of the merge sort then. So it's very efficient for large lists. It's much faster than the other ones that we're going to look at today. And it always takes the same number of steps. So we did it with a little example, but let's say you've got tons of data, it will still take the same amount of steps to actually sort the data. So we've got some disadvantages of the merge sort. It does use more memory. If you were going to code it, it's a little bit more complex. Finally, we're going to have a look at what is called the insertion sort. So it is faster than a bubble sort, because most of them are, but it's slower than the merge sort. If the value that we're checking is smaller than the value that we are looking at, it will keep moving left until it meets a value that is less than it. Once it's in place, we will keep doing that with the next piece of data until all the data is sorted. So to begin with, we've got our data which is unsorted. We're going to start by looking at the 4. That's got nothing to the left of it, so it stays where it is. We then look at the next value, which is the 6. The 6 is larger than the 4, so that's going to stay where it is as well. So our first swap will come in place where we look at the 5. It's going to be compared to the 6. It's smaller than it, so it will swap with it. It then checks it against the 4. It's larger than it, so it'll stay where it is. We're then going to look at our next piece of data, which is the 3. The 3 is smaller than 6, so it will swap. The 3 is smaller than 5, so it will swap. The 3 is smaller than the 4, so it will swap. There's nothing left to compare against, so we'll move to our next piece of data. So the 8 was bigger than the 6, so it stays where it is. So we looked at our next piece of data, which was the 2. It's going to swap with the 8. We compare it to the 6. It's smaller than it, so it's going to swap. The 2 is smaller than 5, so it will swap. The 2 is smaller than 4, so it will swap. The 2 is smaller than 3, so it will swap. Nearly ran out of space on my slide, but that is our sorted data. So let's look at the advantages and disadvantages of an insertion sort. So it performs very well when the data is already almost in order. It's also easy for beginners to learn how to code it. So disadvantages of an insertion sort include, if it's got a large list, it will start to become inefficient and slow down. We've got some questions to practice then on this topic. So question 1, complete a bubble sort on the following. And the next question is, what is an advantage of using a merge sort instead of a bubble sort? So you'll have to compare the two. Okay, let's go through the answers then. So for our bubble sort, you can see the 3 got compared to the 4. There was no swap because 4 is larger than 3. So then the 1 got compared to the 4, which then swapped. 4 then gets compared to 2. It's larger than it, so it's going to swap. 4 gets compared to 5, and there's no swap, and that is 1 pass. We then go back to the beginning. 3 gets compared to the 1. It's going to swap because it's larger than it. And then the 2 gets compared to the 3, and it's going to swap because it's larger than it. And that is our sort done. So for our advantage of using a merge sort instead of a bubble sort, the merge sort is much more efficient with large amounts of data. That'll get you 1 mark. A bubble sort will take much longer. That will get you your 2nd mark.
Today we're looking at searching algorithms. So an algorithm is just a set of rules that can be followed to achieve a task. So when we're using searching algorithms, we're thinking of a set of rules that we can follow so that we can search for a particular piece of data. Now this piece of data could be in some sort of list or array, and it might be good for looking up to see if something already exists in a database or in some sort of data set. Now for your exam, you're going to need to know 2 main searching algorithms, which is the binary search and the linear search. Now for the binary search, we have to be able to perform it and show the steps of it, whereas the linear search, we more just need to be able to talk about and just explain how the steps would work. So let's start with the binary search. Now one of the most important things we need to remember about a binary search is it has something called a prerequisite. This is something that has to have happened before a binary search can take place. So the prerequisite of a binary search is the data has to be sorted first. At each step, it will halve the amount of data that it's got left until it finds what it's looking for. So this is really good for large data sets. A disadvantage is what I've previously mentioned, the fact that the data has to be sorted first before it can take place. But if you've got a really large data set, then it's going to still work out time-wise a lot faster. Another disadvantage would be it's more complex to actually code. So for beginners, it's not going to be an easy job. Let's look at the steps to perform a binary search then. So this is a typical kind of question you might get in your exam. A list of sorted numbers are stored in an array. Show how a binary search would find the number 18. So the very first step we would do is to find the midpoint. You would have a 0-based system. In the actual first position, that is actually position 0. then 1, 2, 3, 4, 5, 6, and 7. Now we need to be able to find our midpoint, and we're going to use a tiny bit of maths to find this point. If you made it clear that you understood that you needed to find the midpoint first, then you didn't need to use the math. So you could just literally write find the midpoint or put a little arrow pointing to the middle point. But if you were going to find the midpoint, we would do the very left side, which is 0, added to the very right side to begin with, which gives us 7. Now we've used a word here, which is div, and we're going to div 2. Now this does mean divide, but because we're using div, it's going to return the whole number only. So in this case, 7 div 2 would give us 3.5, but we're going to ignore the 0.5 because it only returns the whole number. So we found our middle position, which is going to be 3. Now it's a good idea on your exam to actually show what you're doing throughout the steps. So you can actually remove data, put lines through it, put arrows. It's really helpful for the examiner to show your understanding. So in position 3, we are storing the integer 12. Now we know because we sorted this data that it must be greater than that. So at this point we can discard the entire left side, including position 3, because we've already checked there. So all I'm going to do is put a line through it and cross that out, and we're left with this data. Then all you've got to do is repeat the steps until you find what it is that you're looking for. So our new very left position is position 4, added to our very right position, which is position 7. Div 2 is going to give us 5. We know now that it's going to be less than what's in position 5, which was 21. So we're going to discard that whole side on the right, including position 5. At this point, we've only got position 4. That is both our left and right side now. So 4 add 4 gives us 8. Div 2 is going to give us 4. So finally, we are pointing at the position where we wanted to find our data. So you could just write 18 has been found. The next searching algorithm that we're going to look at is a linear search. Now a linear search will start at the very first position and it will just move along one position at a time until it finds what it's looking for, or it reaches the end without finding it. Now the biggest advantage of this is that the data does not need to be sorted first, and it's much easier to program, so it's quite simple to understand. But as a disadvantage, it's much slower on larger lists. So compared to the binary search, which got rid of half the data each time, let's say that the data that you're looking for is right at the end, it's going to take a lot longer to find that piece of data that it's looking for. So for this one, like I said, we don't usually have to show the steps for a linear search, so we just need to be able to explain it instead. So let's look at a practice question together. Explain why a linear search would be more suitable than a binary search when using an unsorted list. So it's only a 2-mark answer, and what you could write is a linear search does not require the list to be sorted. A binary search only works on sorted data, so cannot be used without first sorting. So we've got a question for you to practice using the binary search. A list of sorted numbers is stored in an array. Show how a binary search would find the number 7. Okay, let's go through the answers then. So like before, we need to start by finding our midpoints. We can do this by doing 0, add 8, which is our very left position, added to our very right position. Div 2 is going to give us 4. So 0, 1, 2, 3, and 4. So this is our current midpoint here. Now we know because the data's been sorted that it must be less than that because we are looking for the number 7. So we are going to discard the entire right side, including position 4. Then we're going to use our new left side added to our right side, which is 0 plus 3. Div 2 is going to give us 1. So we are now looking at position 1 and we have found our data. So 7 has been found. That's the end of the question. And that's it for this one. I'll see you next time.